Well, this is module 12. This is game theory in blockchains, and this is the last lecture. Is lecture 4 about proof of stake. And well, the table of contents, we're going to see the proof of stake concept, the main characteristics, and some examples, some networks that use this mechanism. This is in the context of this module about game theory and its application to blockchain. And well, let's see the concept. The learning objectives here is to see the proof of concept, to see the proof of stake concept, its motivation, and so on. Then some characteristics, and finally some examples. Okay, so let's see the proof of stake concept. And the idea here is, before discussing the concept, we need to talk about the motivation of proof of stake. And the idea is of proof of stake is to try to answer this question: can we create a secure and distributed canonical ordering without relying on external energy, like proof of work? I mean, proof of work works because we rely on external energy to create or to generate the blocks. And the idea is that it is difficult to forge because you need a lot of energy to attack the system. But in this case, can we create also a consensus algorithm, but only using on-chain information? This is the question behind proof of stake, and the idea is to change the paradigm of proof of work. The idea in proof of work is that you vote, or you have influence in the system according to your CPU or your processing capabilities. In fact, to your hashing power. But here we are going to change the idea by one coin, one vote. I mean, your capacity on the system, or your influence in the system, or the amount of blocks that you are going to generate on this system depends on the number of coins that you have on the system, and that you devote to this task of generating or forging blocks. So, and this is the idea behind proof of stake. Well, as we will see, proof of stake algorithms are non-trivial. They are quite challenging to design. We're going to just in this lesson, we are just going to provide the general concepts, because, as I said, this type of algorithms are not so trivial. Okay, so again, what is the concept? The idea is that we are going to make a lottery again to select which is the next verifier, or the next node in the network that is going to create a block. And this lottery is going to be run according, or the probability that you win the lottery will be according to the number of coins that each node on the network, or each validator, is staking. To participate in this process of generating or forging or validating blocks, you need to own a certain amount of cryptocurrency, and then you need to publicly express that you want to participate in this process. So, and this is like this because, I mean, you need to to say this because participants need to do some tasks when they are participating in the in these tasks or of validating blocks. So in particular, if you win the lottery, then you will need to create a block, for example, and for this purpose you need to be online and you need to access the transactions and create a block and so on. So not everybody having funds in the system may want to participate. So the fact of staking exactly refers to the fact of validators committing funds to the system for this purpose, and you are committed to follow all the mechanisms in order to create these blocks, like being online, having transactions to put on the blocks, and so on. In many proof-of-stake networks, staking is used to guarantee that you're going to be online from a certain block to another block in the future. And so staked crypto, the part of the staked cryptocurrency is in general is a subset of all the cryptocurrency available. So if we see this more graphically, it's like in proof of work networks we had like users that these users they had cryptocurrency in the system, and then we had miners that they were hashing blocks, trying nonsense to try to mine the block. In the proof of stake is like this, is like merging these two roles, and now we have validators, which are essentially users that have cryptocurrency in the system, but they are also willing to forge or create blocks. So they need to have some type of server or machine that is online, that is following the network, and that is creating blocks when necessary, essentially when you win the lottery. So here in proof of stake, we say that a block is forged or minted, but not mined, because mining comes from proof of work. So it is a concept that now we are not using anymore in proof of stake. So, and when you win the lottery, you essentially create the block, providing a digital signature on this block using your secret key, the secret key associated to the coin that has won the lottery. If you stake more cryptocurrency, then you will have more probabilities to forge more blocks. If you stake less money, then you will have less probabilities of forging or creating these blocks. Well, here we have a lot of questions, because there are different flavors of the proof of stake mechanism for creating the blockchain, and these many systems differ in different aspects. Okay, so well, we need to see which are these aspects, but most of them follow at least this approach. That is, the staking mechanism is something like this. For example, let's consider that we have in the system different users that have money on the system, but in this case only these four, A, B, C, and D, only these four these four parties have decided to participate in the proof of stake mechanism. And even they are participating not with all their money. For example, A has 600 coins, but it is only participating in the staking, in the proof of stake with 500. B is also participating with 500. C and D are participating with 1,000 each. Now, with all this money on the table, we just number all these coins. Okay. For example, let's consider that this is, I don't know, 600, A is put 500, let's say, I don't know, Ether or whatever you want, and then we use the sent ID. For example, this is let's consider that our cryptocurrency has 5 decimal digits, so we put a number to each possible cent of the coin, and we assign when these users here need to send a transaction to the system in which they are committing some coins for staking. Then we assign sent IDs to each of these users. For example, for A has this from this sent ID to this sent ID, 4999.9999, because these are the 500 coins that we are staking, and the rest follow the same idea. Okay, so essentially in this table we have a bunch of cents, and each cent has an identifier and also belongs to one of the entities that has staked this amount of money. And then the idea is that we need some lottery here, just generate a random number that selects one of these cents. For example, I don't know, let's consider that the lottery selects the cent 22554567. Then we go to the table and see to who is the owner of this cent, and the owner of this cent is the one that is going to generate the block in this case. So this is a rather general idea that all the systems follow, but proof of stake systems in fact differ in many different things, and we need to ask many different questions here because different systems do different things in different ways. For example, one question that each proof of stake system needs to solve is how you're going to participate in the generation of the blocks of the system according to the coins that you stake, but then it is important to know how this stake, how the coins are shared among all the participants in the system. Okay, so how this is done. There are systems that, for example, do this at the beginning, or we're going to see different options. Also, we need to discuss a little bit also the incentives for staking. So, which are my incentives for staking? In general, these incentives have to do with the fact that if I am selected as the new validator of a block, then I'm going to receive some fees or maybe some Coinbase from this block. But we need to see which are these rewards and so on. Another question is, how is this random process of selecting the validator. Which factors are considered? Only the stake? Well, this is another important question. Block timing is also important. Another important question is what happens if there are not enough online nodes in the system? So then we cannot generate the next block. So can we delegate our stake to someone else that maybe is online and can generate the block on my behalf? Another question is, should we implement some kind of punishment mechanism for nodes that do not behave properly? And another question, the final question maybe, is okay, the selected validator or forger creates the block or just proposes the block and then we need another mechanism to validate this block. Well, this last question creates in fact a couple of different approaches for the proof of stake mechanism. One is the chain-based, is essentially is like proof of work. When you are selected, you directly create the block. Okay, so these are chain-based proof of stakes mechanism, and the other option are Byzantine fault tolerance style, in which if you are selected, you can be selected as a proposer, but then there is a committee that needs to validate the proposal. So you can be selected for the committee or you can be selected for proposing the block. Well, these are a lot of questions, and in this lesson the idea is to address or discuss some of them, and then, well, that you do some research to try to answer more of them. So let's try to answer some of the questions, and let's go with the first one, which is about distributing the stake. In a proof of stake network, it is very important in the hands of who is the money, because the people that has the money, that has money on the system, is the people that is going to validate blocks. So the security of the system is it depends on the people that has the money. So this is a big issue, and the systems here are more secure as they are as secure as the distribution of the stake and the reputation of the people that is inside the system. Well, the idea then is, okay, how do I highly distribute the stake? Well, there are different approaches here. Some networks decided to use proof of work at the beginning and then change at some point to proof of stake. This is the approach of Ethereum, for example. In Ethereum, they define a first step of the network in which the network is working with proof of work, and then after some time, well, in this case, nearly 10 years, and after the stake is really distributed among a lot of different people, then they switch to proof of stake. There are other systems that start directly with an hybrid mechanism in which there is proof of work and proof of stake at the same time, and then this is also called hybrid proof of stake. And at the beginning, most of the blocks are with the proof of work algorithm, and then as times goes by, the amount of proof of work is is getting lower and lower, and the amount of proof of stake is getting higher and higher, and at the end, all the network finally works completely with proof of stake. Other blockchains, for example, Next, they decided to just sell or share all the stake at the beginning of the blockchain. Well, this is another option. Okay, regarding stake rewards, well, each proof of stake network uses a different way of computing these rewards. What is true is that in general, the creation of new cryptocurrency is minimized regarding proof of work. In proof of work, the reward in each block tends to be high, and then but in proof of stake, tends to be high because miners are doing a lot of work here and they need to be paid. And in proof of stake, the work, the actions that a validator needs to do, that they are not expensive. So mainly in many networks, in many proof of stake networks, the reward it's only due to the fees that users pay. In other systems, there is also some generation, some coin generation. But well, this the exact way in which these things are done depend obviously on the particular blockchain system. Okay. Why some blockchains are generating new coin despite we don't need to generate this new coin to pay for users? Well, this inflation usually tries to encourage that users spend their coins and not hold them to make the cryptocurrency more to increase the usage of the cryptocurrency. Okay, but in any case, block rewards and fees in general in proof of stake are lower than in proof of work, because here we don't have we don't need the amount of energy that you need to participate in the proof of work network that you need to participate in a proof of work network. Some examples of proof of stake networks. Well, the original idea of proof of stake was developed in Peercoin, in PPC, in 2013, but currently we have many different flavors of proof of stake networks. For example, NXT or Blackcoin or Cardano, or now Ethereum. Ethereum is also running with proof of stake, Algorand, etc. Okay. So let's discuss a little bit some of these systems, and we're going to discuss chain-based proof of stake approaches, and see that essentially we are going to see that it's not so easy to design a system like this, even though you try to imitate what proof of work is doing. That here we have problems that in proof of work where did not appear. Okay, so let's start with some chain-based proof of stake, and let's see how it works. So here the idea is that there is some pseudo-random process to choose a validator. In this process, as we said, the selected validator is going to be chosen according to the amount of staked cryptocurrency, and the winner of this lottery just creates a block creates a block pointing to the previous block and sends this to the network. Well, this is roughly the same idea as proof of work. And in proof of work, this lottery was created according to a work that you need to do, that a hash, you needed to hash. In proof of work, you need to hash the block together with the nonce to obtain a number of zeros at the beginning of the output. Okay. We can also see this like k. I mean that this hash has to be smaller than k times d, where k is the output space of the hash function. I mean, k is all the k is if the hash function is a SHA-256, then the possibilities of this function is 2 to the power of 256. And then we have the difficulty. If the difficulty is 1, it means that I need to do a hash, and the hash needs to be smaller than 2 to the power of 256. So for sure that we are going to hash and obtain this. So difficulty 1 is in fact the least possible difficulty. And then if I put, for example, 2 here, it means that I hash. If I put difficulty 2, it means that I need a 0 in the first bit of the hash, and so on. Okay, so this is the formula for the proof of work algorithm. So if the difficulty is higher and higher, then this number is smaller, and then you need to hash something that has more zeros at the beginning, in the most significant bits. Well, the idea of the first generation of proof of stake algorithms was to do something very similar, but instead of hashing with a nonce and doing tries, essentially you hash with you use the block, the hash of the previous block, your sent ID, and some timestamp, and then you check. And well, timestamps, the timestamps that you can choose is these are not so many, okay? And essentially you check if you win the lottery by doing this hash operation here, and if you win, then you will generate the block, okay? But the problem is that two different validators may do this hash and may obtain a value that is less than this k times over d, and then we may have like two winners. This also may happen in proof of work. And the problem here, if there are two validators that win the lottery, well, we should only select one canonical history. So one of this is a split in the network, but we need to agree on one of these two blocks. In the case of proof of work, this is automatically done by the algorithm, because well, the first when a new block appears, essentially is selecting which of these which branch do we need to use. But and essentially when you are doing proof of work, you need to decide on which of the two branches you put your resources. But the problem here is that validators here could not decide one of the branches and just keep trying to see, just keep operating over the two branches at the same time. Okay, putting all their stake in both branches. So here we need. There is nothing. This problem is called nothing at stake, and it means you don't risk anything by just keep working on the two branches at the same time. Okay, you don't lose anything if you keep working at the two branches at the same time. And this is a problem. This is a problem because we need to just create one blockchain. We need a canonical history here of my blockchain. So how do we fix this? Well, the idea is that if you follow two branches, then you need to lose some money. Okay, so we need to penalize. Well, this is how in proof of work is fixed, but in proof of stake we also need to make it expensive to follow a non-canonical chain. Okay, and how do we do this? Well, in fact, by slashing. Okay, this is typically the way of doing this. If anybody is following, if I see that you are forging blocks in two branches at the same time, for example, then I can slash part of your staked coin, because you are not contributing to one stable history, but you are in fact you are unstabilizing the network. Okay, so there are a certain amount of situations in which we can use slashing, slash the amount of stake, just to penalize people that is not behaving correctly. And this is and now you have something at stake. If you forge a block on, if you create blocks on two branches, this is not good because the network is not stable. You are not contributing to the stability of the network, so you get slashed. And the idea is that there are people outside the network which they are taking a look at what is happening, and if they send a proof to the network that someone is misbehaving or bad behaving, then this entity gets slashed, and part of this money goes to the node that is monitoring and is actively trying to detect these bad behaviors. So, proof of stake networks, as you may see, are much more complicated than proof of work because since there is no real heavy work, we need external. We need to monitor the network. We need to reward people to monitor the network, and so on. So these systems get much more complex. And what things do we check, or which behaviors must be disincentivized? Well, for example, creating bad blocks, or creating splits, or forging or creating blocks in multiple branches or forks, maybe creating blocks in the wrong chain, etc. Or, for example, not forging the block when required. You are offline and you should be online to create the block, and so on. Okay, so we need to force the users to have something in stake, something to lose if they don't behave correctly. Okay, and the mechanism to force this is slashing. To implement slashing properly, then we need to pay people, pay these monitor nodes. We need to properly pay to these monitor nodes that are monitoring the network, and so the currency, the cryptocurrency, needs to have some economic value to pay these monitor to pay to these users or to these monitor nodes. So if our proof of stake network is not highly viable, then we cannot properly pay the monitor nodes, and our network is less secure. The more value of the cryptocurrency, the best we pay to all the nodes in the network that are doing all the different tasks, and the better protected the network is. So in some ways, economics protecting economics, and the network needs to have enough economic worth to protect itself. Okay, well, this is like this is represented with this figure here, okay, which is the network protecting itself in some way, or beating itself. Okay, and essentially this concludes this briefly introduction to proof of stake. We discussed the proof of stake motivation, essentially get rid of proof of work, because proof of work is consuming a lot of energy, a lot of power. We discussed the proof of stake concept, in which the coins that you own on the system is the thing that you use to enter in the lottery of being a validator for blocks. We talk about the stake distribution. So it is important that the stake is distributed and in the best possible way. And then we discuss a little bit some issues, some aspects of the chain-based proof of stake, some problems like nothing at stake, in which you can, if you don't implement any slashing mechanism, then you don't have incentives to stabilize the network, and you, for example, can generate blocks in different branches or forks. And then we talk about the slashing, which is a mechanism in which we have people taking a look at the network, and if they manage to see a bad situation and manage to prove this situation, they will receive part of the penalty of the party that is misbehaving. And this mechanism is slashing. And we conclude that if our blockchain doesn't have enough value, then all these mechanisms are hard to implement, because if you don't pay if you don't pay to the nodes that are securing the network, if you don't pay enough, your network is not going to be secure enough. If you pay good and design good mechanisms, then the proof of stake network can work. And that concludes this section, and that's all. Thank you so much.